Good day, guys. Welcome to another video on how to carry out some quantum calculations using Gauss view and Gaussian. So, in the last class, on the last session, we learned how to set up our molecules or how to set up how to set up our calculations on molecules using Gauss view. But now we are going to see, or today's video, we are going to carry out a practical overview of what we learned in the last class. We are going to carry out a practical session on what we informed us about the last class. So here we'll be carrying out optimization calculations on some molecules, on a single molecule using different choice and basis sets to check how accurate they are using the DFT approach. We make use of the DFT method using three different basis sets, and then we check out how the results can be compared with the experimental variables. Um, right, so without taking much of our time, let me open the software, Gauss View. Yeah, so I think the software has opened. Right. So let's try modeling for our compound of interest. So let me quickly do that. All right, then let me look for an oxygen atom. All right, let's place that here. Let's come here once more. Let's look for a chlorine atom. All right, we can place that at the top here. Then let's look for a methyl group. Let's choose carbon at our own discretion. And yeah, the molecule is already modeled. So this molecule is 1-chloroethanol. 1-chloroethanol. It's a chiral molecule because it has no plane of symmetry. It's the central carbon is attached to four different functional groups. So it's a system that consists of 9 atoms and 42 electrons. Now the question is, why did I choose? Oh, sorry, escape. And the question should be, why did I choose this compound? The reason why I chose this compound is because it has fewer number of electrons. 42 electrons is still fair enough. So it's still fair enough because the more bulkier the electronic system, the longer our calculation takes. The longer the calculation takes. The longer the calculation takes. So that's the reason why I decided to use a very small electronic system to showcase or to practicalize based on what we've learned previously. So we are going to set up our molecule for calculation. And how do we go about that? I told us in the last class we can go about that using two different routes. You can either come here, select, and also select Gaussian calculation setup, or we can use our keyboard by clicking on Ctrl plus G. So here we have the calculation. We've accessed the Gaussian calculation setup icon. Then we come to job type because we want to perform optimization calculation. Before any other calculation, it's best for an individual to first perform optimization calculation before calculating for any other thing. Optimization is very important because you have to optimize the molecule to bring it down to the ground state before you can perform any other operation on the molecule. So we'll be looking at optimization calculation, and we won't change anything at this point. We leave all of these guys as default and minimum. You don't need to change anything. Then we leave this as ground state. Now we want to perform a DFT calculation. We select the DFT. We leave the our choice of method as Pk 3D and par. Then we select, let's use the 321G, and then let's just select the plus, and do we polarize? Let's polarize here. So the polarization function is, as you can see, is in form of a star. So yeah, we've polarized for the heavy atoms that are there. I only polarized for the heavy atoms. That's the reason why you see the star. Yeah, I polarized for the heavy atoms. The heavy atoms, that is carbon, oxygen, chlorine, and this other carbon, are being polarized for. So there's no need to change anything here. So I can write this as um chloro. We can title our work as chloroethanol. Yeah, that is chloroethanol. Then we place an hyphen in order to make it clear. 3 2. We can say we can place an hyphen 3, or we can place it in a bracket. Maybe I should place in a bracket and replace 3, sorry, 3 hyphen 2 at a writing 3 hyphen 2 1, then capital letter G. So that's being done. I have a reason why I saved it as that. I also press on Control C. I have a reason for clicking on Control C. I will show us the reason why. Then we come to link. Then perhaps I want to change the processors into 4 processors to make the calculation very fast. So then I can come to what else again? I think that's all. I don't need to add any more thing. We leave every of those guys as defaults. We don't change anything there. Then I come to preview. Then I think after I must have done that, yeah. Then I can come to, yeah, let's come to submit. Yeah, then I like to save. But where do I want it to save? I can come to, I have a Gaussian folder already opened on my system, but I want to save this particular folder in a different I want to save this particular calculation in a new folder. So how do I go about that? I think I should come to my computer. No, should I? Yeah, I think. Or users document or user. Maybe you should come to user. Then I come to desktop. Then I can create a new folder. And what should we name the folder? Let's name the folder chloroethanol. Chloroethanol. So yeah. And after naming the folder, then yeah. Yeah, the file name. What I want to save the name as. Sorry for going blank. I have not yet saved the file. The reason why I copied the other time was because I knew that this was still going to pop up. I want to save this file now. So I will paste the name of the file from that title, the name I have titled it initially. So I paste here. So we can see it has popped up. Then I click on save. It is asking me a question. Notify when the job has finished. I click on yes. Now let's see what happens. Can we say the calculation has started on the molecule? So Gaussian has started. Um, Gaussian has started performing the calculation on our molecule. Right. So as we can see, the software is performing the calculations and 42 electronic system. Wow. So you can see how maybe in the next 2 or 3 minutes the calculation will end up. All right. Okay. It's taking longer than expected, but we have to exercise patience, even with four processors. Hmm. All right, the job has completed. I didn't even know it would take this long, but yeah, we can open the job now. You can see the icon that has opened now. The CHK file has been selected. Let me also select the log file too so that we can check together and open. Now it told us that we're having two set of files. We have the log file, we have the CHK file. Now, oh, wow, this is interesting. Okay, I'm seeing something unusual here, like the hydrogen bond, the chlorine bond has broken. Aha. On the log file, while on the CHK file, we have the chlorine bond still intact. All right, this is interesting. One of the chlorine atom broke at a point. The bond that is on the carbon to chlorine bond is breaking on the log file, whereas on the CHK file, it still remains intact. So it's one of the funny, or uh, this is one of the things that we would observe about aha, about choosing busy set. But well, let's talk about the log file and the CHK file. The CHK file, the log file makes me has access to the steps Gaussian took while making those particular calculations. In a nutshell, I can open the log file with Notepad, but I cannot open the CHK file with the Notepad. So the CHK file, but I can perform some operations on the CHK file that I can't perform on the log file, like visualizing molecular orbitals, checking out the electrostatic potential map, DSP map to know how the electrons are quite distributed in space, and many other things. I can do that on the CHK file, but I can't do that on the log file. But the log file can make me have access to the step Gaussian took. Each step Gaussian took to computing those calculations until it got to the endpoint. So let me show us what I am trying to see using, about the log file. Now let me exit and then let me go to the working directory, the working directory and show us what I mean. So let me come here, yeah, and then let me um, uh, show us um, where did I place it? I think it was on the local disk. No, not local disk. Yeah, this desktop, right? Desktop, and then on desktop we have. I think I opened the file that says, didn't it say? Yeah, chloroethanol. And we can see the three files have been located. We can see this is the input file, this is the Gaussian output file, this is the C log file. The log file is the output file, while this is the checkpoint file. So it comes with .log. If we check, let me show you something. If we check the name or the properties of this file, let's check the name. You will see that it comes with, no, not this. I think the properties, it should come with .log. Can we see the type of file? Gaussian output file .log. So this is the log file. So right. So what I'm trying to say is that we can open both the log file with Gaussian or Notepad. Let me see. Now I can open with Notepad. Why can I open with Notepad? Remember I told us that we can open with Notepad because so as to check each step Gaussian took towards computing those calculations. Now, can we see each step? These are the steps taken by Gaussian to perform those particular calculations. These are each of the steps. So we can go through the log file. Perhaps we can even have an idea of what went wrong on that particular molecule that made the bond break. So the log file will give us that particular information, or we can check the step that it took that made the bond break. So that's that about the log file. So the CHK file we can check all around, all to the last step. Can we see? The steps are much. So we can imagine if we are to do for all of these theoretically with our hands. So thank God we now live in an age where we have high graphical processing units, IGM systems that have high computing power that can perform these calculations. So all we just need to do is to just write some set of algorithm that can perform this task. So yeah, okay. Can we see how long it is? So this is how long until it get. These are the steps. So meaning that if an human being were to compute this manually, it might take him weeks. It take him weeks before he gets to the last step. Hmm. So I want us to just see until we get to the very end. Perhaps maybe I should stop scrolling so we can come down to the very end. So this is where the calculation ended. At this point, this is where the calculation ended. And one thing that is very interesting about Gaussian is that after performing the calculations, they place a quote at the end of the every calculation. So this is the computation. This is the job computational time. This is the job central processing unit time. So it might be different in our own realm. In our own realm, a job might take 3 days, but the CPU realm, it might take a day. So according to the CPU, based on the CPU calculations, the CPU calculation on the CPU, the calculation might just be a day or 22 hours, whereas you spent 3 days performing that particular calculation. So it's quite that's where quantum mechanics is. It's very interesting. So yeah, so that's that about the log file. Then the CHK file. You see, once I open the CHK file, it just takes me automatically to Gaussian. It opens Gaussian straight. It opens it up straight. So I can perform several operations on this CHK file. So yeah, I can do a lot of things. I can come down to results. Can you see the results now? Can you see a lot of things are now accessible for me to check? I can check the charge distribution. I can check the atomic properties. I can check the bond properties. I can check the surface contours. I can check the molecule group table, and yeah, lots more. I can even check the summary of the results. If I want to check the summary of the result, I can just click on this and then let's see. Does it have a dipole moment? Yes. Wow, has a large dipole moment. That's 1.947004. So this gives us that particular summary. That is the root mean square gradient norm 0.0007 at So the unit for anything electronic energy, the energy here is also computed in at3 energy. So the energy here is in at3. So this is the basic set that we did. Calculation type, can we see optimization calculation? This is the file type is the CHK. This was the basic set that we used to carry out the calculation. The charge, the spin is a singlet state. So it's very interesting. So the molecule has no charge. So we can see that the charge on it is 0. So that's very one thing that is quite interesting about this. So we can come here to the result, and if I don't want to come here, I can just come here, right click, then select on the results here, and then the same thing that I have accessible there would also be accessible there too from inside. We can check the atomic properties and bond properties. Okay, now let's check. You can show the number. We can even show colors. We can check the color boxes to look at the color range, symmetric range, and then fixed range. So we can uncheck these boxes. You can see that they are confusing us. Yeah. If we want the number, it can show us the number. We can check the bond length between the carbon to chlorine is very long. The carbon to hydrogen here is long. Perhaps maybe that is the reason why that one it broke on the log file because of the unusual, the abnormal length. Perhaps that's the reason why it broke. So you have the 1.477, 0.994. So these are the bond length. If I desire to show colors, you see that a wide range of colors would be fixed. You can see 1.87, very large. It's a long bond length. The color range is even very green, it's pure green. So you have 1.44. 1.44 is intermediate, is greenish too. Yeah, so 1.5, you can see the color too. The hydrogens are short, 1.0s, and yeah. So we can check a lot of things under um that. So we can also come to, let's come to result again. Let's look at the atomic properties. We can check what are the properties of the atom. So yeah, and check that 1.00, hydrogen 7 is 1.00. This is carbon 1 is 6.00. So this is also 6.00. Is that 17? I'm saying 17.00. We can check. I think the numbers that are attached to that. So we can choose to change the color. Our color ranges here. We check that everything changes. We check the symmetry range color, fixed range color. Yeah. So it gets quite that's one of the amazing aspects about this. Let's close. And I can come here. I think the result again, term properties. Let's close. So let's come again to results. We have the bond properties, you have the charge distribution. Let's check the charge distribution. Let's check the number of the charge. Okay, look at the charge distribution. 2.0, is that 0. I can't see clearly. 0.294, 0.432. So these are the distribution of the charges. Let's color them by range so that we'll be able to identify. Wow. So we can check, or we can note the ones that are negative and the ones that are, wow, minus 0.002. That's the oxygen. So we can check a lot of things using this. We can do a lot of things on this particular software. So it gets interesting. So on this note, I would like to just stop here. So our next video would be how to carry out this quantum calculation using another basis set, the double zeta basis set 631G. Thank you.